Hello everybody. We have discussed about some topics on partial differentiation such as function, then limit of the function, continuity of the function, then partial differentiation. Now we shall study the total differential of the function, then composite function. Or let us give the definition or define the total differentiation. Let z is equal to f of xy be a function of two variables. The total differential of the function z is equal to f of xy is denoted as dz or df, and it is defined as dz is equal to del z by del x times dx plus del z by del y times dy. Let us take one example related to finding the total differential of the function. First example, find the total differential of z is equal to f of xy, which is x square y plus 3 at the point 1, 2. Solution: the total differential of the function z is equal to f of xy at ab is given as dz is equal to del z by del x at the point a, b dx plus del z by del y at the point a, b dy. Here we have the function z is equal to x square y plus 3, and the given point a, b is 1, 2. Now we have to find del z by del x and del z by del y for this function z is equal to x square y plus 3 at the point 1, 2. So let us find del z by del x. So derivative of z function with respect to x is twice x, y is constant, so twice xy. So this is twice xy, and if we put x is equal to 1 and y is equal to 2, so we get 2 times 1 times 2, so it is del z by del x at the point 1, 2 is 4. Now we find del z by del y at the point 1, 2. So the function is x square y plus 3. So differentiating this partially with respect to y, so x square is constant, partial differentiation of y with respect to y is 1, here also 1, so x square plus 1 is the partial derivative of z with respect to y, so x square plus 1. Now we substitute x is equal to 1 and y is equal to 2, so there is no y here, so we can write del z by del y at the point 1, 2 is equal to 1 plus 1, so 2. Thus we substitute the value of del z by del x and del z by del y in dz, so we get dz is equal to 4 times dx plus 2 times dy. So this is the total differential of the given function z is equal to x square y plus 3. Okay, now let us take another example. Find the total differential of z is equal to f of xy, which is equal to log x of x by y at the point 1, 1. So we know that the total differential of the function z is equal to f of xy at the point a, b is given as dz is equal to del z by del x at the point a, b dx plus del z by del y at the point a, b dy. Now here our function z is equal to log x by y, and given point ab is 1, 1. Now we find the partial derivative of this function z with respect to x. So this function can be treated as log x minus log y. So partial derivative of log x is 1 upon x, and partial derivative of log y with respect to x is 0. So del z by del x del z by del x is 1 upon x. And if we substitute x is equal to 1 and y is equal to 1, this is the typing error, so 1 here, del z by del x at the point 1 comma 1 is equal to 1. And similarly, if we find del z by del y at the point 1 1, del z by del y at of the function log x by y, so del z by del y is partial differentiation of log x minus log y, and partial derivative of log x with respect to y is 0, and partial derivative of log y is 1 upon y. So we can get del z by del y is equal to minus 1 upon y. So del z by del y at point 1 1 is also minus 1. Thus the total, if we substitute the value of del z by del x and del z by del y at point 1 1 is equal to, and del z by del y at the point 1 1 is minus 1, so we get dz is equal to dx minus dy. So this is the total differential for the function z is equal to log x minus y. Okay, now we define the differentiable function. So a function z is equal to f of xy is said to be differentiable at AB if it satisfies dz is equal to del z by del x at the point AB dx plus del z by del y at the point AB at dy. If the function is differentiable at every point of the domain, then the function is called differentiable function throughout the domain. We know that the continuity of partial derivative implies the differentiability of the function. That means if the partial derivative of the function f are continuous throughout an open region R, then the function is differentiable at every point. Differentiable function implies the continuity of the function. If the function z is equal to f of xy of two variable x and y is differentiable at the point a comma b, then the function is continuous at the point a comma b. Thus the continuity of the partial derivatives of the function assure the continuity and differentiability of the function. Now we define the composite function and the chain rule for those functions. Let us consider a function w is equal to f of xy of two variables. Further, we have x as function of t, so x is equal to xt, and y is a function of t, so y is equal to yt are two functions of one variable t. Then the function w is equal to f of xt comma yt is called composite function of one variable t. And if all three variable functions are differentiable functions, then we can find out the derivative of w function with respect to t by this rule. So it is dw by dt is equal to del w by del x and dx by dt plus dw by dy multiplied by dy by dt. Here w is equal to f of xy is a function of two variable, so here we write del w by del x, because whenever we have the function of two variables we write del in place of d for function of one variable, and the derivative is called partial derivative. Here dx by dt is there because x is function of t only, so we write dx by dt instead of dw by dx. Okay, now we take another case for composite function. Suppose all are the function of two variables. That means let w is equal to f of x comma y is a function of two variables. Further, x is function of s and t of two variables, y is function of s and t of two variables. Then the function w will become the composite function of s and t, because if we substitute the value of x and y in terms of t in this function, then we ultimately get w as a function of s and t. So that's why we call it composite function of t. W alone is not here. W is alone is not a function of s and t, but all three functions together become function of s and t. That's why we call it composite function of t. And if all the three functions are differentiable functions, then we can find out partial derivative of w with respect to s and partial derivative of w with respect to t by this rule. So del w by del s is equal to del w by del x into del x by del s plus del w by del y into del y by del s. And we can find out the partial derivative of w with respect to t, which is del w by del t is equal to del w by del x by del t plus del w by del x y and del y by del t. Now we take another case. Suppose we have w function of three variable x, y, z, that is w is equal to f of x comma y comma z, and x is function of t, one variable only, y is function of t, z is function of t. These are the three functions of three variables, one variables. Then w and three functions together makes w as a function of t. So we say that w is a composite function of t. By looking this w alone, we cannot say that w is function of t, but all three equations together says that w is a function of t. That's why we call it composite function of t. After the composition of three functions, we get w in terms of t. That is why we call it composite function of t. Now if all these four functions w, x, y and z are differentiable function, then we can find out the partial derivative of w with respect to x, with respect to y, with respect to z also, and we can find out the derivative of w with respect to t by using the formula dw by dt is equal to dw by del x, del w by del x into dx by dt plus del w by del y into dy by dt plus del w by del z into dz by dt. Now we discuss the another case in which w function is of three variable and each of the three variable are again the function of two variables s and t. That means if w is equal to f of x comma y comma z is a function of 3 variables. Further, x is function of s and t, that means x is equal to s comma t, and y is equal to y of s comma t are functions, and again z is also the function of s and t. Then w is a function of s and t, and we can find out the partial derivative of w with respect to s and with respect to t if all 4 functions w, y, x, y and z are differentiable function. So we get del w by del x, del w by del s as del w by del x into del x by del s plus del w by del y into del y by del s plus del w by del z into del z by del s. And similarly we can find del w by del t. Here we have to consider the w function and find out the partial derivative with respect to x, y and z. Okay, so we are finding partial derivative of w function with respect to each of the variables. So del w by del x, del w by del y and del w by del z. Here we are getting x, y, z, but we require here partial derivative of w with respect to t. So we from x we require t, so we are differentiating x with respect to t. So we are getting del w by del x into del x by del t. Here we are getting y from w, but we require t also. So after getting y from w, we are taking t from y. So del w by del y into del y by del t, and del w by del z into del z by del t. It is like that. If we have w in 3 variables x, y, z, and each is the function of, so we are collecting all the variables from w. So x, y and z are collected, and from each of the variable t is collected. So del w by del x by del t. Here we are collecting y from w and then t from y, and here also. So this is the different cases for composite functions. We can consider also different cases. Now let us take some example. So first example, if u is equal to y square minus 4ax, x is equal to at square, y is equal to 2at, then we want to find out du by dt. So it is like that. U is function of x and y, and x and y are function of t, and we want to collect t from u. So we first collect x and y from u. So we collect x and y from u, and after getting x we are collecting t from x. So and t is function of one variable, so we write dx by dt. First I am showing how to prepare the formula. Suppose we have u is a function of 2 variables x and y, so we have to find out partial derivative with respect to x and with respect to y. After getting x from u, we are collecting t from x. So we have del u by del x and dx by dt. Here we are writing dx by dt because x is function of one variable t only. So in case of function of one variable, differentiation is called derivative, and it is denoted as dx by dt. But if function is of 2 variable, then differentiation is known as partial differentiation, and we denote it or we use it del u by del x because u is function of 2 variable. So here du by dt can be obtained by this formula, del u by del x into del x dx by dt plus del u by del y into dy by dt. Suppose this is denoted as equation number 1, we then find partial derivative of u with respect to x and y from here. So here u is y square minus 4ax. If we differentiate partially with respect to x, this derivative, partial derivative of y square with respect to x becomes 0, and 4a minus 4a is constant, and partial derivative of this x with respect to x is 1. So ultimately del u by del x is equal to minus 4a. Similarly, we can find out del u by del y as 2y, and partial derivative of this minus 4x becomes 0. So ultimately we get del u by del y is equal to 2y. Then we find dx by dt and dy by dt. So x is equal to at square is given. So derivative of x with respect to t is denoted as dx by dt, and it is a is constant and derivative of t square is twice t. So ultimately we get dx by dt is equal to 2at and dy by dt as 2a. Now substituting these values in this equation, we get du by dt is equal to, this is minus 4a for del u by del x, so minus 4a, and this is 2at, so this is dx by dt, and del u by del y, it is 2y, so 2y is substituted, and then dy by dt, so it is twice a. So after simplification we get minus 4a into 2at, so minus 8a square t plus 4ay. Now we substitute the value of y also, so y is twice at, so we get minus 8a square t plus 4a into twice at, so minus 8a square t plus 8a square t is equal to 0. So ultimately we get du by dt as 0. Now we take another example for composite function. Example 2. If w is equal to x into e raised to y, x is equal to r cos theta, y is equal to r sin theta, then find del w by del r and del w by del theta. Clearly w is function of two variables x and y. If we substitute x and y in terms of r and theta, w will be composite function of r and theta. So we can prepare the formula for del w by del r and del w by del theta. So del w by del r, for that we need to find r from w wherever it is. So first we collect all the variables from w. So w have two variables x and y, so we collect x from w and y from w. After collecting or getting x and y from w, we want to collect r from the variable of x. So we are multiplying del x by del r, del w by del y times del y by del r. This is the formula. Clearly here I explain again. See, we are collecting all the variables from w. So x and y are two variables, x and y are two variables, so we are collecting x and y from w. After getting x and y, here we are getting x, so from this x we need to collect r, so del x by del r, and here we are getting y, so we need to collect r from y, so ultimately del y by del r. So this is the formula. Now we have to find out each of the partial derivative, del w by del x by del r, del w by del y by del r from this. So here w is equal to x into e raised to y. So del w by del x is derivative of x is 1, e raised to y is as it is, so e raised to y is the partial derivative of w with respect to x. Similarly, we can find out partial derivative of w with respect to y. So del w by del y is equal to, x is constant, so we keep it as it is, and partial derivative of e raised to y with respect to y is e raised to y. So we get del w by del y is equal to x e raised to y. Now we have to find out del x by del r and del y by del r. So we take here x is equal to r cos theta and differentiating partially with respect to r. So partial derivative of r with respect to r is 1 and cos theta is constant. So we get del x by del r as cos theta. And from here y is equal to r sin theta. So partial derivative of r with respect to r is 1, sin theta is multiplied with r, so we keep it as it is. So del y by del r is equal to sin theta, substituting these values in this result. Okay, so del w by del r is equal to e raised to y into cos theta, and this is del w by del y, so it is x into e raised to y, and this is del y by del r, so it is sin theta. So simplifying this, e raised to y is common from both the terms, so e raised to y is equal to, this is del w by del r is equal to e raised to y is common factor from both the terms, so cos theta plus x times sin theta. Now we substitute the value of y as r sin theta and value of x as r cos theta. So we get del w by del r as e raised to r sin theta times cos theta plus r cos theta sin theta. So we get del w by del r. Here cos theta is again common factor, so we are taking it outside. So cos theta e raised to r sin theta 1 plus r sin theta, this is there. Similarly, we can find out del w by del theta by substituting the value of del x by del theta and del y by del theta in the formula of del w by del theta, which is del w by del x times del x by del theta, del w by del y into del y by del theta. So it is very clear that we are collecting theta from all of the variable of w. So here w has two variables, x and y, so we are taking partial derivative of w with respect to x with respect to y, and then from x we are getting theta and from y we are getting theta. So the formula becomes del w by del x by del theta plus del w by del y into del y by del theta. Therefore we get del w by del theta is equal to, this is the value of del w by del x, which is e raised to y into minus r sin theta plus x into e raised to y r cos theta. So from both the terms we are getting e raised to y common and then multiplied by minus r sin theta into r square cos square theta if we substitute the value of x here. So x is r cos theta and r cos theta, so r square cos square theta. Therefore we are getting del w by del theta is equal to r into e raised to r sine theta multiplied by minus sine theta plus r cos square theta. This way we are finding the partial derivative of w with respect to r and with respect to theta. Now we take another example. Suppose u is a function of one variable r and r is equal to cos t, y is equal to r sine t. Then prove that uxx plus uyy is equal to f double dash r plus 1 upon r into f of r. Since we have u is a function of one variable r, so u is equal to f of r, we can simply apply the chain rule for function of one variable. But here r is function of two variables, so ultimately u is function of r and r is function of x and y. So from u we can get x as well as y also, so del u by del x. So here u is a function of one variable, so here it will be du by dr, and du by dr is multiplied by del r by del x. Here we have to write d. Why? Because u is function of one variable, so this is du by dr and then del r by del x. Similarly, we can find out del u by del y as du by dr into del r by del y, and we have r square is equal to x square plus y square, so we can find partial derivative with respect to x from this equation. So twice r into del r by del x is equal to twice x, and r is taken on the other side, so 2x upon 2r, 2 will be cancelled out. So ultimately we are getting del r by del x is equal to x by r and del r by del y. For that we are differentiating this partially with respect to y, so 2r into del r by del y is equal to 2y, so 2 will be cancelled out from both the side, and we get del r by del y is equal to y by r. Substituting these values in this result, del du by dr will be also denoted as du by dr, or will also denoted as f dash r. So after substitution we get del u by del x as f dash r into x by r. Suppose this is the result number 3. So differentiating 3 partially with respect to x. So here we have r is function of x and y, x is also function of x, and r is again function of x and y. So we have to apply u into v into w rule. So according to that rule we have to differentiate f dash r and keep this 2 as constant. Then we keep f dash r and 1 upon r as constant, differentiate this x, and finally we are differentiating f dash, we are differentiating 1 upon r with respect to r. So del square u by del x square, derivative of f dash r is f double dash r into del r by del x. This is with respect to r and this is with respect to x. So ultimately we are getting x from f. So f double dash r into del r by del x, and these 2 are as it is for this term x and r. Now we keep f dash r and 1 upon r fixed, and partial derivative of x with respect to x is 1. So second term is this f dash r into 1 upon r. Now we keep f dash r and x fixed for a while, and derivative of 1 upon r with respect to x is minus 1 upon r square into del r by del x. but we know that del r by del x as x by r. So we are substituting this value and this value in this. So we are getting this x by r, and here also x by r. So square of this f double dash r as it is. Here f dash r 1 upon r, f dash r as it is, x minus x upon r square, and here we are getting this del r by del x as x by r. So finally we are getting del square u by del x square is equal to x square upon r square into f double dash r plus f dash r into 1 upon r plus f dash r into minus x square upon r cube. Suppose this is the result number 4. Now we need to find out partial derivative of u with respect to y. So del u by del r is equal to f dash r into y by r. We have already calculated this. Now again differentiating 5 with respect to y. So del square u by del y square is equal to f double dash r into del r by del y into y by r plus f dash r is a constant for this term, and partial derivative of y with respect to y is 1, and 1 upon r is constant, plus f dash r and y is kept fixed, and derivative of 1 upon r with respect to y is minus 1 upon r square del r by del y. Now we substitute the value of del r by del y as a y by r here and here. So we get del r by del y as y by r, so y by r square. So del square u by del y square is equal to f double dash r into y by r square plus f dash r into 1 upon r plus f dash r into minus y upon r square into y by r. So ultimately we get del square u by del y square is equal to y square upon r square into f double dash r plus f dash r into 1 upon r plus f dash r into minus y square upon r cube. This is say result number 6. Now we are adding 4 and 6 to get del square u by del x square plus del square u by del y square. So del square u by del x square plus del square u by del y square. So here if we check, then here del square u by del x square, in case of del square u by del x square, here x square upon r square, and in case of del square u by del y square, here y square upon r square, and f double dash r common for both the terms. So we are getting this as first term. So f double dash r into x square upon r square plus y square upon r square. Okay, now in case of del square u by del x square, f dash r into 1 upon r, and del square u by del y square as 1 upon r, and ultimately we get f dash r is 2 by r minus 1 by r. So del square u by del x square plus del square u by del y square is equal to f double dash r plus f dash r into 1 upon r. So we proved this. Now we define implicit function. So implicit function is a function of the form f of xy is equal to 0, because here after some simplification we can consider y in terms of x. So y is expressed in terms of x, and that's why we say that y is implicitly expressed in terms of y. That's why we call it f of xy as function of x, and similarly for x also. So ultimately we are not making it clear that x is function of y or y is function of x, but if we, for the next concept, we assume that x is independent variable and y is depending on x. So let us consider one theorem. If f of xy is equal to 0, then dy by dx is equal to minus, here minus sign is skipped, fx upon fy, and d square y by dx square is equal to fxx, here also minus sign is there, fxx into fy square minus 2 fxy into fx into fy minus fyy into fx square, and here fy cube. Proof is very simple enough. Since we have f of xy is equal to 0, so differentiating partially with respect to x, so del f by del x into dx by dx plus del f by del y into dy by dx is equal to 0. So del f by del x plus del f by del y is equal to into dy by dx is equal to 0. So we get del f by del y into dy by dx is equal to minus of del f by del x. So fy into dy by dx is equal to minus fx. Therefore we are getting dy by dx into minus fx upon fy. Similarly, if we differentiate with respect to x again, so we have to apply the u by v rule, and we are getting this formula, and substituting the values of dy by dx, we are getting minus fx upon fy, and finally we get this formula. Here minus sign is missing, so minus sign is also there. Let us take one example. If x cube plus y cube minus 3xy is equal to 0, then we want to find dy by dx. So we know that f of xy is equal to 0. This is f of xy is equal to 0. So dy by dx is equal to minus fx upon fy, and d square y by dx square is equal to minus fy square fy whole square fx square minus twice fx fy into fxy plus fx whole square into fy square upon fy cube. First we find fx fy and fx square and fxy. So partially differentiating this function with respect to x, we get fx as 3x square minus 3y, and again differentiating this function with respect to x, this is 6x and derivative of this is 0. So similarly we get partial derivative of y with respect to partial derivative of fy with respect to x as minus 3. Substituting these values, we get dy by dx is equal to minus 3x square minus 3y upon 3y square minus 3x. After simplification, we get minus x square minus y upon y square minus x. And similarly, if we substitute d square y by dx square, we are finding the value of d square y by dx square as minus 54xy upon 27y square minus ax. So today we have discussed about composite function and implicit function. From the composite function, we prepare how to find the partial derivative of given function with respect to its variable, and from implicit function we are finding the derivative of one variable with respect to another variable. Thank you.